one of the things that we want to do is define all of our words. And you'll see when I'm doing problems on the board, word problems especially, I'll be defining things as we go along. And all the things that I talk about in class, I want to make sure that we have a careful definition, because some words are used in plain English slightly differently than what we would use in math. So I'm going to go over a couple definitions and then get into the material of linear equations. So first off, an equation is a statement that equates two expressions. Now an expression is just something like this, 2n plus 2, or x plus 5, or something like that. That it has some sort of value if you assign a value to your variables, but it really doesn't do anything. It's like a phrase in a sentence or something. But what an equation does is it takes two of these expressions and says these things are equal. And so, so equation and expression have two really quite different meanings. So what we're going to talk about here is a linear equation in one variable. And so we're going to make kind of seems like a little obscure definition here. We're going to say it's any equation that we can write in the standard form of ax plus b equals 0, where a doesn't equal 0. You see, if a equaled 0, we would just have b equals 0, and that's no fun. And then we're also going to say that a and b are real numbers. So we're going to be dealing with one variable. It can be x, it can be something else. A and b in this case are numbers, constants. And so anything that we can put into this form is considered a linear equation in one variable. And so when we solve an equation, what it means is that we're going to find all the values for which x for the statement is true. So if you have an equation, you might find one or more numbers that make that true, or you might not find any. Okay? So if the solution set, and by solution set I mean what you get when you solve an equation, you get a solution set, or the solution. If it's all real numbers, if any number that you put in for your variable works, okay, you stick in any number, you call that an identity. So for example, the simplest identity would be x equals x, because regardless of what x is, it'll equal itself, right? So if x equals x is your statement, 3 equals 3, if x equals 3, well that works, that's true. It works for all real numbers, so x equals x is perhaps the simplest identity. Okay, now if we have a solution set that includes only some real numbers, we call this equation a conditional equation. So an equation is true only if, and here's the condition, if you have certain values for x. Only certain values are a part of that solution set. And then of course the only other possible case that we have is if there's no solution, we'll call it a contradiction. And it's possible you have equations that simply have no solution. All right. So the key words there are all, some, or no. And this is very typical in mathematical definitions, that some doesn't mean all and all doesn't mean some. And all that. You have to be very careful and very precise about how you make your definitions. And so it's easy to look at the big words in a definition, but key ones are going to be all or some or none. Okay. So first thing we're going to see is if we have a value, do we have a solution? And so we do this by substituting the value directly into the equation. Now I know this probably seems kind of simple at this point, all right? So this one we solve by saying, okay, 5 times 2 equals 9. Now notice what I did here. I wrote this equation and it wasn't perhaps scrolled out in the same way that I would normally write it, but the way you make a substitution, the most reliable way of making a substitution, is rewrite the equation, and then where you have the variable that you want to make the substitution, because you might be in a case where you're going to substitute expressions, not just numbers, write the whole thing with just parentheses instead of the variable. So you can start out by doing this. Okay, there's your equation. And instead of the variables, I'm writing a little space with the parentheses, and then just stick whatever x is in there, and you get that. And so especially where you have more complicated equations and expressions, making a substitution like this is really reliable because you're only doing one thing. You're not trying to keep track of signs. You're not trying to do multiplication in your head. Nothing is going on except actually doing the substitution, and then we take care of the math. So in this one, okay, 5 times 2 is 10. 10 plus 9 equals 4. This is obviously not right, so we call this not a solution. So if we try a different number, like let's say -1, we'll do the same thing. We substitute the -1 in the equation, and then simplify it out, and we find 4 equals 4, so yes, indeed, that is a solution. So the thing about testing a solution like this is that it tells you that this particular value is a solution. It doesn't necessarily tell you that it's every solution, okay? And so one of the things about sometimes guessing at solutions in mathematical equations is that you might guess one of the solutions, but you won't guess all of them. Now, it just so happens that in linear equations like this, if you have one solution, you have exactly one. You can have infinitely many, exactly one, or none. And so, so that's really not too much of a case here where x equals -1. It may be that every number works, but we've already demonstrated that. But here only one number works, so that will be the unique solution to this equation. All right, so that's just pretty much testing potential solutions. How do we find the solution? Now, what I just showed you, that particular equation, that 5x plus 9 equals 4, is fairly simple, and I know a lot of you will do these things with a minimum of writing. But what I'd like to do is go over the properties or the principles that you can use to solve these, because whenever you're solving equations, these are the only things that are allowed. It's, you know, a lot of people will think of this as whatever you do to one side, you do to the other. And that is kind of true for multiplication and addition, but on other things, like square roots or some other functions, that may not be true. So we have to be careful, just like we have careful definitions, we have to carefully obey our rules. And then once we understand those rules, then of course we can start making abbreviations around that. But the properties that we have 4 of them. Number 1 is that we can simplify either side. So if we have an expression like, or an equation like 4x minus x equals 8, the expression on the left-hand side of this equation can be simplified. 4x minus x equals 3x. Okay, so that might seem obvious, but nevertheless, that's one of the things that's allowable in this case. The second thing is that we can add to both sides, add any real number to both sides. So it can be 0. If you add 0 to both sides, you may not get you anywhere, but it's still a valid thing to do. In this case, what you want to do is take a look at what you want to do from a long-term standpoint and kind of select what you add, and there's really no restrictions on the numbers. So here I have an x minus 5 equals 2. I want to simplify that left side to be only x, so the way to simplify that is add 5 to it, so you got to do both sides, add 5 to both sides. And then you can multiply both sides, but now multiplication has some restrictions. Okay, so here if I have 3x equals 12, I can multiply both sides by 1/3, and 1/3 times 3 is 1, so we can just say x there. 1/3 times 12 is 4. So here I'm multiplying by the reciprocal of 3. That's the same thing as dividing by 3. So there's really 2 values that you can't use when you're multiplying both sides. One of them is 0. You can take any equation and multiply both sides by 0, and you end up with 0 equals 0, which is really, you've lost all the meaning of your equation. And it's not necessarily equivalent either. Because if we have 4 equals 9, which is obviously wrong, we can multiply both sides by 0 and we get 0 equals 0, which is true. And so multiplying both sides by 0, first of all, is not productive, but even if you do it, it'll be misleading if you try and get any meaning out of it. Yes?
Real quick, for simplify either side, when you take out an x, does not leave you with 3x minus 1 equals 8? This isn't technically 4x minus 1x equals 8.
No, 4x minus x is 3x, right?
Oh, that's right. 3x. I was thinking you were dividing by x.
No. No, if I divided by x, I would have
8 over x,
yeah, 4 minus 1 over x, or
Yeah.
something like that. But that's okay. Okay, very good. So we have to be careful. We can't multiply both sides by 0, and we can't divide both sides by 0, because division by 0 is not defined. It's just not a number, and it's not going to be helpful to us. So we have to be careful with multiplication around zeros, but of course with addition, it doesn't really matter. You can add or subtract 0. It's just not going to change your equation much. And then the very last thing to do is something that happens pretty easily. You can change the sides. 12 equals x doesn't really roll off the tongue as the same as x equals 12, because you're usually trying to find x, and so unless you speak like Yoda or something, you order your sentences in kind of a standard way. So this is possible. The other reason why you may want to do this is just from a practical standpoint on your page. If you have a very long expression equals something else, a simple expression, you can switch it around so the simple expression equals the longer expression, because working on the right side, you have a little bit more margin. You don't have to exactly guess how much space you need because you got all the way to the end of the page. So you can do it from a purely practical standpoint like this, or maybe it just rolls off the tongue a little better, x equals 12. There's no reason that you have to do this, though. Certainly at the bottom of a problem, I can understand that 12 equals x equals the same thing as x equals 12, but you're free to interchange sides. The equality means both sides are the same, so one can go in place of the other. And so really, with these linear equations, these are the 4 things that you can do. There's nothing else that you do beyond these 4 things. So let me take an example, and I'm starting out with simple examples here. So we have this equation in standard form. Now you can probably do this one in your head if you look at it, right? Or at least most of you can. But let's look at it from the standpoint of applying these properties. Okay, so the first thing I'm going to do is I'm going to subtract 15 from both sides. And so that was one of our 4 rules. Next thing I'm going to do is simplify, and that was part of the 4 rules. That was the first rule. And then we're going to divide by 3. That was the 3rd rule. And then, of course, we simplify, and we get x equals negative 5. So even though perhaps on a page you could do this, perhaps the next line you would write after that 3x plus 15 is just 3x equals negative 15, and then x equals negative 5. You might take that kind of a shortcut. What you're really doing are those 4 steps. Okay, so moving something from one side to the other is adding the same or subtracting the same thing from both sides. Now this will become more important as we get more complicated kind of expressions with polynomials and things of that sort. And sometimes there's some techniques like completing the square where adding 0 is going to be used, and instead of adding 0, you're adding 5 minus 5, which is 0, but you have some need for a 5 in there. And so there's other ways to manipulate this, but for linear equations, this is what we're doing. All right. Okay, so you try this one. You can probably do this one in your head, but just write it down and think about the steps that you're doing as you're doing it. Okay, anybody want to describe what they did? Yes,
Add 12 to both sides,
okay,
and then you have 7x equals 12, and then you divide by 7, so you have x equals 12 over 7.
okay, very good. And if I write all those things out the long way, this is what I get. But what you described, 2 lines is probably what it took you to
Yeah.
write it, excuse me, my English is bad, is perfectly fine. Now, notice that you stop at 12/7, and I think I mentioned this to you on Wednesday, but I want you to start treating numbers very carefully. And so 12/7 is a really good number, okay? So we want to leave it as a reduced improper fraction. And the reason why we do this is because most of the time when you're doing algebraic manipulations, you're not going to just do a single calculation. You'll be doing more. And so perhaps you need to find x to substitute it in an equation to find, you know, some practical calculation or something of that sort. 12/7 will be the easiest thing for you to use. So x equals 12 over 7. Now you can also write it as 1 5/7, and that's not too bad. If that's your final answer, that's probably a pretty good answer, because people will have to think 12/7. Is that more than 1, more than 2, more than 3? You know, there's a little bit of math that you do in your head. So as a final answer, 1 5/7 isn't too bad either. But it gets confusing because when you're doing algebra, because if you have, let's say, 6 5/7, oftentimes when you're writing algebra, that means 6 times 5/7. And of course, you write an improper fraction the same way you write without a multiplication sign 6 times the fraction. So this isn't too bad if it's the final answer. Okay, the one that you shouldn't do is this one. 1.714, because it's inexact. Now, ultimately, this will repeat somehow, and there's ways of notating repeating by either putting a bar over what repeats, or you put ... after you've established the repetition pattern. But that's kind of a pain to do. If you round it off, it's going to be inexact. And especially when you're doing scientific work, like if you're going to study chemistry or biology or something like that, and you start rounding off numbers at every step that you take or every intermediate calculation you do, the rounding ultimately has an impact on how accurate your calculation is. You should never, ever round before you're finished with your calculation. So even if you're only measuring something, let's say weights to the nearest tenth of a pound or so, you should keep all the digits that you have all the way along the line until the very end, and then round it to an appropriate number. So here in an algebra class, since we're not dealing with generally scientific numbers, we want to stick at 12/7. Okay? Okay, so here's another one. Okay, anybody actually want to come to the board and do this one? A little bit of writing? Anybody? Come on up. Write big. Yeah, go ahead. Describe what you've done.
So I subtracted 9y from both sides. And then added 2 to both sides. All in one go here, just for the sake of time. 6 is 3y. Then you divide by 3. 2 equals y.
Great. Okay. I don't know where it went either. There it is. Okay, thank you. Now, he did some notation things that are very common and that are just fine. One of them was that he's manipulating the equation kind of vertically, where he puts what he's going to do to both sides. And that's fine, so long as you don't put an equal sign here, because these two, well, they do equal each other, but that's really not the point of what you're doing. So it's a nice compact way to do multiple steps all at once, so you just add these vertically and you end up with a 6 and 3y. Divide both sides by 3, don't have to rewrite it, and you get your answer. Now, one of the things that I think you should think about when you have something like this is that you want to bring the term with the variable in it to whichever side it's positive. So he subtracted 9y from both sides. If this were bigger than this, then you would subtract this one from both sides. It still works if you do it by making the negative one on, or if you end up with a negative coefficient. It all works, but there's just one less thing that you have to deal with if you favor the side that'll give you the positive coefficient. So that's more how to do it more quickly, kind of a tip than an actual requirement. All right, so then subtract the 9, y, simplify it, add 2, simplify it, and then divide by 3, and you get y equals 2, exactly the same thing. Okay? Okay, so we can check these by substituting it back in. Occasionally I might ask you to check it, but oftentimes you'll get answers that are fractions, and the checking is more complicated than the actual solving it, so I'm not going to torture with you by making you check everything, because I know the checking sometimes is harder than the actual solving. Okay, so let's deal with fractions. Now, let's say we have this equation that involves a couple fractions. There's a few ways that you can do this. One of them is just to do it the same way that we've done all of these, and then when it comes to actually simplifying the fractions, adding them together, you find the common denominator, and then you go from there. And that works, but I think it's a little bit more work than you need to do. Personally, I think equations with only integers in them are the easiest equations to work with. So the method that I'm going to show you here, perhaps you've seen it before, but here I'm going to eliminate the fraction first. Okay, so the thing that you want to do is find the least common denominator, or not least, but lowest, I guess is the actual phrase, lowest common denominator. Just like you would if you were trying to get manipulate the fractions. So you do this by factoring everything that's in the denominator. We have a 15 in the denominator. We have a 10 in the denominator. Okay, so 3 times 5, 2 times 5. And then what we do is we identify what's in common between the two of them. In this case, it's 5. And then we find the lowest common denominator by taking what's in common, and you only use it once, and then you multiply it by each of the unique factors, and so you'll get your lowest common denominator is 30 here. So that's useful. Now, you don't always have to even multiply it out. In fact, sometimes you don't want to multiply it out, but you identify what the lowest common denominator is. And we're going to take that then and multiply both sides by that number. And so for this particular equation, we're just going to take both sides, multiply them by 30. And then we're going to get 30z plus 30 over 15 equals negative 90 over 10. And so when we simplify that, we actually get integers. Now, when I said that you didn't even need to multiply out the lowest common denominator, it'll save you a couple steps, because working with larger numbers is harder than working with smaller numbers. So if I did this by just keeping the 5 times 2 times 3, what I can do is, okay, here I'm going to have to multiply it out, so I get the 30z, But before I do the multiplication, I can already cancel out the 5 and the 3, and this just becomes 2, right? Because it's 5 times 2 times 3 over 5 times 3. Well, that cancels and we get a 2. Same thing here. The 5 times 2 cancels out the 10, and so we have 3 times 3 is negative 9. And that's where we are there. So especially with big numbers, leave things factored, because it's when you have a product in the numerator of a fraction, it's almost always easier to factor and do the division before you actually extend the multiplication. So that's one way you get around the fact that I don't let you use a calculator here, is that do the division first with integers, and then you're dealing with smaller numbers. Okay, so we just finish this one off and we find that z equals negative 11/30. So even though the solution is in a fraction, most of the work that we've done was just with integers. So that, for me, always works a little easier. Any questions so far? Okay, so you got to try this one then. All right, so just to recap what he did, you factor it, find the LCD as, you have that 2 in common as a factor between the two of them, and then you multiply it by all the remaining unique factors, and then from here you multiply both sides by 24, and then you simplify those ratios, and then we get 7t equals 24, t equals 24/7. Very good. Okay? All right. Let's talk about decimals. Now, occasionally, when you're doing a measurement or something, it'll come out, you'll have decimals. Like when you do, a weight, you'll oftentimes have something like 10.5 pounds, or if you're doing a financial calculations, you'll have $7.23, or anything that involves decimals. So you're going to be using decimals frequently in life. So there's an easy way to deal with decimals in linear equations, and it has to do exactly with the same principle here, where we're multiplying through by essentially a common denominator. And the common denominator in this case would be always some multiple of 10, 100, 1,000, something of that sort. So let's say we have this equation here where we have 6.5 times 1 minus 2x equals 13. So you notice we have the 0.5, so we multiply both sides by 10. And then when we simplify that, we get 65 times 1 minus 2x equals 130. And be careful not to overwork this. The 10 is, we have two factors that we're multiplying 10 by, so we only multiply one of them. It's not a case where we're going to distribute something. Okay, so in other words, when I have something like this of course is going to be 10a plus 10b. But if I have 10 times a times b, which is that case where b is that factor 1 minus 2x, this is just going to be 10a times b. Okay, so don't multiply things more than they need to be multiplied. So we end up with this 65 times that factor equals 130, and now we expand it, and we get, we subtract 65 from both sides, and simplify that, and then we divide by 130, and we reduce that to negative 1/2. And this is a perfectly good answer, but in this case too, whoops, I guess I didn't write it down. I had intended to write down. Negative 0.5 would be appropriate here. And it's appropriate because you started with decimals, and so it's okay to answer in decimals. You know, it's kind of like saying the preferred language is English, and so we answer all the questions in English. But you know, somebody asks you something in Spanish, it's probably the preferred way to answer them is to answer them in Spanish, right? And the same thing with kind of the form of our numbers, that if we have a problem that's stated with decimals, there's certainly nothing wrong, in this case, in answering with decimals. Okay, so here's one for you. You try that. I flipped back to the last screen because I paused the recordings while you're doing things, and I realized I hadn't resumed it. So if you go there, go back to the recordings on YouTube, you'll miss the explanation on how the last problem solved. So at least you get, you know, a screen capture of what the solution was, if that's the case. So I don't have a producer with me, so I have to kind of do it on the fly. Okay, so what'd you find here? Yes? No solution, okay. And so what told you that it was no solution?
Because it has zero. Has the zero. It says 0 equals 9 on that.
Okay, so you had an equation that was clearly not true, right? Not possibly true. And I think I came up with the exact same thing, that 0 equals 9. Right? And so that's not possible. 0 doesn't equal 9. All right, so I'm going to mark that it doesn't equal 9, and I'm going to write no solution. And that's all you need to do, is indicate that there's no solution. Now, once you get practiced at this, you'll notice that probably about the second line, 3x minus 6 equals 3x plus 3, if you subtract the 3x from both sides, you get negative 6 equals 3. And that's a perfectly good contradiction as well. And so oftentimes when you have infinite solutions or no solutions, sometimes the calculation is much shorter than if you're actually trying to find the solution. So let's change this by a little bit and say it's, instead of x plus 1 on the right, let's say it's x minus 2. Okay, so work ahead a little bit on that one. Okay, and what did you get? Did you get something, Nick?
Oh, yeah, I got it right now. Yeah, 3x equals 3x, so just 1 equals 1, right?
Mm-hmm. But you go from 3x equals 3x to either 0 is 0, but I don't know how you get 1 out of 1 equals 1.
Right if you divide, I didn't do it that much, like 3x.
Yeah, if you divide both sides by 3x, then you get 1 equals 1. Okay. So the long way to do it. Now, right here, you got 3x minus 6 equals 3x minus 6. Those are the same things, right? That's the same expression on both sides. It's appropriate to stop here and just call this infinitely many solutions. Okay, if you really want to prove the point, you can go through and do the rest of the calculation, and you can work it all the way down to 0 equals 0. And you can do that. But like I said, it's perfectly good to stop where it's obviously the same thing and then write infinitely many solutions, okay? And so 3 ways to write this. You can write it as an identity. An identity means that it's the same thing, that any value, that statement is true. You can write it as true for any x, or you can say infinitely many solutions. All 3 of them are just fine. I kind of formatted it to make them look a little different, that the two dots are explaining what an identity means. But it's perfectly fine to say, you know, as your final answer, true for any x or infinitely many solutions. Okay? All right, so here's one in that vein for you to try.
Because it ended up being just not equal to 0.
Okay, so you had something that was obviously not true, that couldn't be true. So you probably did something like this. Or maybe you kept the fractions, because if you subtract 2/3 from both sides, 2/3 x from both sides, it'll actually drop out to 4 equals -2. But if you do it the long way, you find this, and so you get, it's a contradiction or no solution. So did you see what I mean at the beginning? When you have the same term on both sides and there's only constants after that, you can do a perfectly legal reduction of this thing just by subtracting 2/3 x from both sides, and you get 4 equals -2. And so that can't be, and so you write no solution after that. So it's a single step. So it's worth your while sometimes to inspect an equation and kind of look at what's going on there before you just start cranking out, you know, the steps that make it kind of a more routine kind of a question. So oftentimes you can short circuit the solution. You can get to it much faster by doing something like that. Okay, any questions here? All right, how about the next one? Try this one. Let's look at the step-by-step here. So I distribute the 5 on the left and I distribute the 4 on the right. And so the first thing I'm going to do then is simplify the left side. Now here's a perfectly good place to stop. This is an identity, or infinitely many solutions. Okay, so then if you want to really reduce it down to nothing, you can continue going on and you get 0 equals 0. So you have infinitely many solutions here. But like I said, you're perfectly free to stop at this point, because it's obvious when you read the equation that you have one expression equals the same expression. That's just as obvious as x equals x, okay?